In this segment, we will talk about control charts. And so these are run charts, but they have also control limits. Now, control chart methodology originated in the manufacturing environment, but has also been used in healthcare settings a lot in the last 10, 20, or maybe 30 years. And so here we have a study in an outpatient settings about patient waiting times to see a specialist physician. The study period was 4 weeks, and for each day in those 4 weeks, we have 30 patient waiting times recorded. The staff of the clinic were not made aware of this study. So here's a question for you. Why do you think that is? They had enough to do and don't need to be burdened with additional information? Or they might try to change their behavior for the period of data collection? Or they might actually be uncomfortable and might interfere with the data collection effort. I will leave that up to you to answer. And we are looking a bit at the data. Here we have the 20 days for the 4 weeks. We have the run length called R here, which you would have called the sample size for each day. So 30 observations, waiting times for each day. Then we have the average for each day and the standard deviation for each day estimated. Now, it's kind of hard to find what's unusual on this chart. So we look at the graph. And so here we have a run chart. Okay, and so we see some variability in here and something looks maybe unusual, but are they so unusual as to be unlikely to be true, or there being some problem or issue or something to understand? And to do that, we need to find control limits. Now, control limits are exactly the same as confidence limits here, with one specific level of confidence. The control charts are also called Shoehard charts after their inventor, Walter Shoehard. And you can do these things for individual observations, but if you plot them for averages, and here we collected, we have an average for each day, then they are called X-bar charts for the obvious reason. So control chart theory is a grand word in this context, because all we're doing is we have a normal distribution, and for each day we have a different mean and a different standard deviation. And we are saying it's in control if the different means refer to the same overall mean and the different standard deviations refer to the same overall standard deviation. In this example, I will just look at the means. The standard deviations can be looked at also, but I will concentrate on the means here. All right, so given data, we can test the hypothesis. Mu I equals the overall mean mu, and I can test that for each different day. Then we get the usual statistic here. In the denominator, we have sigma divided by square root of R, because we have an average over R observations, right? So this would be 20 in the case, in this example, well, because we have, no, 20 or 30. I think we have 30 observations for each day, so it would be 30. And the standard practice is to say a process is out of control if D is greater than 3. So if we are 3 standard deviations away from the mean. And this is maybe the only difference to a confidence limit. We are specifically looking at 3 standard deviations, whereas a confidence limit exists for 95%, for 90%, for 99%, and so forth, right? Well, let's see what level of confidence this corresponds to. And this is as usual, once we standardize this is a normal distribution, Gaussian 0, 1. And then we can compute the confidence limit, and we can see that the alpha here is 0.0027, or in other words, we have 3 out of 1,000 false alarms, false out of control signals. If we think about, we have 1 per day here, right? 1 chart per day. So 1 year has about 226 or so working days. When you subtract holidays and vacation and so forth, you are in the neighborhood of 226. And that means that 1,000 days would be a little over 4 years. And we're getting 3 false alarms in 4 years, so less than 1 false alarm per year. That seems pretty reasonable to get 1 false alarm per year. So just to get a sense of what that means. Okay, so we do that in this case. We compute the control limits, we plot them, and we see 3 points out of control. Okay, so when they're out of control, then we say there is special cause here. It's out of control due to special cause. If they're in control here, there is natural variation, and that's due to common cause. And once they're out of control, it's due to special cause. We don't know what that special cause is. Now we need to go to the manufacturing floor and investigate. The terms special cause and common cause are, it's just terminology here. All right, I said this already. One thing to keep in mind is an in-control process, we still need to monitor and have maintenance once in a while, check up on it in the same way that if your car runs fine, you still want to do an oil check every once in a while, or oil change, because that keeps the car running fine. So these 3 out of control points, of course, go into the computation of the mean and of the standard deviation. So if we think those are special or problem, then we might want to take them out of the computation and just compute the standard deviation and the mean based on all the remaining observations here plotted in green. And when we do that, the control limit is narrower, the mean shifts just a little bit, and we see there's a 4th point that is out of control. Now we have to do this again. So I take this point out and then compute everything based on the remaining 16 points. And now we get something that is nicely in control. Of course, we have the 4 out of control points up there. Question for you. Can you explain these 4 out of control subgroups? Well, if we were in class, I would actually talk to you, but since I can't do that, I will give you the answer on the next slide. What's happening here is they show up in regular intervals, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and so forth. It's always the 5th. Now, 5th means there's 5 working days in a week. And I didn't tell you that, but it starts on a Monday, so this is always every Friday. Well, it doesn't matter when you start. It's the same day of the week every day, every week. And it turns out that the patient mix on Fridays at the specialist was different than on the other days, with an unusually large number of patients from the cardiology department. And those patients require EKGs, which take more time. And that was the reason. And those fun investigations you can only make when you have access to the underlying process on the floor or in the hospital. All right. So I want to remind ourselves about specification limits. We didn't have a specification limit here. We had a control limit. Those are different concepts. Specification is externally imposed by management or by a customer, like remember recycling in China, and they want a minimum purity of the recycled material coming to China. And so the purpose of a control chart is to verify whether the process is stable. A stable process may routinely exceed specifications, right? We get the same amount of impurity in the recycling in here, and it's always too much for China, which is reasonable. And an unstable process may wander around, but it may have so little variation, and the specifications may be generous that it meets specifications all the time. So those are two different concepts. In summary, the X bar chart is useful to detect shifts in the process mean. The control limits are constructed just like confidence intervals, but specifically as these 3 sigma control limits. So it's exactly analogous to confidence intervals in hypothesis testing. And from the chart, we see whether special cause has occurred, meaning points are outside of the confidence intervals, but we don't know what it is. We need to look at the manufacturing floor or in the hospital to check what's going on. And in an ideal hypothetical world, you could do this immediately and correct the problem right when it occurs. That is the end of this segment.